Hello students and welcome to the lecture. So students, as we know that since last two lectures we have been covering the viscosity or we have been discussing on the viscosity. Basically so far we have done with the two parts, part 1 and 2. In this lecture we are going to start with the part 3 of viscosity. Okay? I hope that you have revised the previous two parts in the well enough manner before you have come for this part, as many times I have told you that is for your own benefit. In this lecture, we will going to talk about the Bernoulli's theorem and also the application of Bernoulli's theorem. So these two areas are going to be the point of discussion for us in this particular lecture. But before starting the lecture, actually we have a small disclaimer over here that we are required to understand. The images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this tag and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the images. Now, let's begin with the topic Bernoulli's theorem. So basically, Bernoulli's theorem is actually an outcome of the principle of conservation of energy that is applied to liquid in motion. Okay, this is the statement. Remember it. Bernoulli's theorem is actually the outcome of the principle of conservation of energy applied to a liquid in motion. This theorem states that for the streamlined flow of an ideal liquid, we are talking about ideal liquid, we are not talking about the realistic scenarios, but ideal liquid. The total energy, which is the sum of the pressure energy, potential energy, and the kinetic energy that are usually conserved in the liquid, per unit mass remains constant at every cross section throughout the liquid flow. Like we are saying, as the water in a motion, okay, and passing through the cross sections, okay, so throughout the liquid flow, per unit mass remains constant at every cross section, okay, which means total energy, sum of the pressure energy, potential energy, and kinetic energy per unit mass is remains constant at every cross section throughout the liquid flow. It's not getting changed. So that is the Bernoulli's theorem, and it is actually, as we know, based on the principle of conservation of energy applied to the liquid in motion. This statement is based on the assumption that there is no loss of energy due to the friction. Like we know, whenever a liquid is in the motion, there is a backward dragging force, there is a internal resistance, or we could also call it as a friction. Okay, so what is this friction actually doing? This friction is actually stopping the flow of liquid. Okay, and as the flow of liquid is being opposed, so there may be a loss of some energy due to the friction. Okay, so basically this statement is based on the assumption that there is no loss of energy due to friction. Okay, mathematically, for unit mass of fluid flowing through a pipe, we could say P by plus GH plus 1 by 2 V square equals to constant. This mathematical statement of Bernoulli's theorem is known as Bernoulli's equation. Okay, so if you ever ask like what do you mean by the Bernoulli's equation, remember that this mathematical statement is actually the Bernoulli's theorem. Mathematically, it is presented as like this. Theoretically, we have just seen it. Like when the liquid is in the motion, pressure energy, kinetic energy, and potential energy, the sum of all these per unit mass crossing the cross section remains same. Okay. Now, let's have a look on other forms of Bernoulli's theorem. What are the other forms of Bernoulli's theorem? So, first form is this that you can see here. By multiplying both the side by P. This gives us another statement of Bernoulli's theorem. In a streamlined flow of an ideal liquid, the sum of pressure energy per unit volume, potential energy per unit volume, and kinetic energy per unit volume. Here, remember, sum of pressure energy per unit volume, potential energy per unit volume, and kinetic energy per unit volume remains always constant at all cross section of the liquid. Okay, and remember, this is we talking about as an ideal liquid. This is to be mentioned. Okay, please remember that ideal liquid is mentioned while talking about the Bernoulli's theorem. So we could say P by Pg plus H plus 1 by 2 V square by 2G equals to constant miniding by G. Here P by Pg is called pressure head, H is called gravitational head, and V square by 2G is called the velocity head. Since all the three quantities have the dimensions of distance, hence the name head. According to this equation, Bernoulli's theorem states as in the streamlined flow of an ideal liquid, sum of pressure head, gravitational head, and velocity head at every cross section of liquid is remains constant. Okay, that is not going to change. That is the Bernoulli's theorem. If the liquid is flowing through a horizontal tube, two ends of the liquid are at the same level. Therefore, there is no gravitational head. Therefore, H equals to 0. Then P plus a half into PV, P equals to 0 and constant. This shows that if P increases, V decreases and vice versa. Like when the pressure increases, the velocity decreases, and when the pressure decreases, the velocity increases. This Bernoulli's theorem also states that in streamlined flow of an ideal liquid through a horizontal tube, velocity increases where the pressure decreases and vice versa. And when the pressure decreases, the velocity increases. This Bernoulli's theorem also states that in streamlined flow of an ideal liquid through a horizontal tube, velocity increases where pressure decreases and vice versa, like the same thing that I have told you. When the pressure increases, the velocity decreases, and when the pressure decreases, the velocity increases. Okay, this is also called Bernoulli's principle. Now here we have talked about the Bernoulli's theorem. Let's have a talk like what is the limitation of Bernoulli's theorem. Like we know every theory is having some advantages and disadvantages, or you can say having some applications and limitations. So now it's a turn for the Bernoulli's theorem. Like what are the limitation of Bernoulli's theorem? First, while deriving the Bernoulli's equation, it is assumed that velocity of every particle of liquid across any cross section of tube is uniform. Okay, velocity of every particle liquid across any cross section of tube is uniform. That is actually the basic assumption of Bernoulli's equation. That is the first limitation. Practically it is not correct. Okay, second, in fact, the particles of the liquid in the innermost, therefore the center layer, have maximum velocity, and those on a layer in contact with the tube have least velocity. Now let's take back a tour to the first lecture. Why I'm saying let's take back the tour to the first lecture? Any guess? Okay. In the first lecture, if you remember, when we were talking about this, I had told you one thing. Whenever the liquid flows, okay, so the center layer always having a maximum velocity, always having a maximum velocity, and the upper layer that is in the contact with the wall of the tube having a least velocity. Even we had seen a picture where the arrows used to show the direction of the flow and velocity. The mid arrow, the midiest arrow having a high point, and the uppermost arrow and the lowermost arrow having a low point. to indicate the least velocities. Here in the Bernoulli's equation, what we are assuming that velocity of every particle of liquid across any cross section is uniform. What we are assuming, this is what we are assuming. Practically, what we have seen that the central layer having a maximum velocity and the layers which are in contact with the tube having a least velocity, having the least velocity. Therefore, we should take the mean velocity of the liquid. We couldn't be depend on that. This viscous track of the liquid which comes into play when the liquid is in motion has not been taken into account. Like in the ideal fuel, or you can say not fuel, in the ideal fluid, we say that the viscous track, the backward dragging force is negligible. Okay, so that's why the viscous track that happens in the liquid, we not take this in account while we say the liquid is in flow. While driving the above equation, it is assumed that there is no loss of energy when liquid is in motion. Why? Because the viscous track we have not taken it into consideration. And when we are not taking it into the consideration, automatically we are not taking the consideration of any loss of energy that could be happen when the liquid is in motion. Automatically that will happen. In fact, some kinetic energy is converted into heat and it's lost. Like practically, if we go to the practical situations, we could say liquid having the backward driving force because they having the viscosity. Okay, like if they are in a motion, the relative motion between the layers will be opposed because of the backward dragging force, because of the internal resistance, because of the friction. And when there will be a two opposite forces acting on each other, one force is basically pushing the liquid in motion, one force is dragging back it. Okay, so viscous track is actually results in K conversion into heat and lost. So in the Bernoulli's theorem, we are saying that the pressure energy, potential energy and kinetic energy will remain same. Will remain same. There will be a no loss of energy. Practically, this is not happen. Practically, some of the kinetic energy converted into heat and some of the kinetic energy getting lost, which means that the sum of them is not uniform. It is changing. Okay, and when the sum is changing, so no loss of energy when liquid is in motion is not a practical statement. There is a loss of energy when liquid is in motion. Okay, if the liquid is flowing along a curved path, energy due to centrifugal force should also be considered. Okay, now after talking about the Bernoulli's theorem, we have talked about the limitations also, the applications also. Now, sorry, we have talked about the limitations and also the statements of Bernoulli's theorem. Now let's have a look over the application of Bernoulli's theorem, where the Bernoulli theorem applicates or applies. First, airfoil, lift of an aeroplane. So any surface designed so as to obtain reacting force from the air through which it moves is called an airfoil. It becomes possible because the characteristic shape of the airfoil is shown in the figure. Here you can see it. The upper face of airfoil is more curved than the lower one. Like if you talk about it, you will see this curve is lesser curve in comparison with the topmost curve. That is the same thing written here. Upper face of airfoil is more curved than the lower face. That we could also see in this figure. When streamlines flow past the airfoil, they split up at the leading edge but join again at the trailing edge. Like here you can see. This is the separation point. So they are getting separate here, but again they are getting joined together. Okay. These streamlines above the airfoil follow the curvature of the surface of airfoil closely, but those at increasing distance from the surface become crowded. Like here you can say those which are having the increasing distance from each other, they are becoming crowded. Therefore, in accordance with the equation of continuity, as the cross-sectional area of the tube of flow above the airfoil decreases, the velocity of the air increases. The application of Bernoulli's theorem tells that the pressure above the air should decreases as the velocity of the air has increased. Thus, due to typically shape of airfoil, the pressure above the airfoil becomes less than that in the region below the foil. So if we talk about this, suppose this is an airplane, so the pressure here and the pressure here. Okay, so in the upside the pressure is less and lower side the pressure is more. The difference of pressure between upper and lower surface of the airfoil gives rise to an upward lift because it's become easy to go upward and even the low pressure drag the thing on upside. It is called the dynamic lift on the airfoil and maintain it in air against the gravity. In case the airfoil incline upwards a few degrees with respect to the direction of air, the air striking the lower surface is deflected upwards and its reaction gives an additional lift to the airfoil. But if the angle increase, the airflow does not remain steady and turbulence is setting. Okay. Now, second is atomizer or sprayer. An atomizer is usually used in perfume and deodorant bottles. When the rubber balloon is pressed, air passes with a large velocity over the tube, dipping in the liquid to be sprayed. Due to this, pressure over the tube dipping in the liquid decreases. It makes the liquid rise up in the tube. Due to the applied pressure, the air rushing out with a large velocity from the balloon blows away the liquid coming out of the nozzle in the form of a fine spray. Here you can see this in the picture also. This is the rubber balloon, this is the fine of the spray, and this is the liquid. Blowing off the roofs of houses during a storm. In a storm, cyclone, or hurricane. Okay. Sometimes the light roofs of thatched houses are blown off. Due to the high velocity winds blowing over the roof, the pressure over the roof increases. Here you can say this is the high velocity. The pressure over the roofs keeps on increasing. That's why it's got detached and it's got blown off with the flow of air. As the atmospheric pressure below the roof is greater than the pressure above the roof, the roofs get tilted and is blown away by the wind. A person standing near the railway track is pulled towards the train when a fast moving train passes close to him. Here you can see in this picture. The fast train decreases the pressure between the person and the train so that the person gets attracted towards the train's motion. Due to the greater value of the pressure on the other side of the person gets pushed towards the railway track. Two ships sailing in the ocean get pulled towards each other if they come close to each other. Why? Because the pressure between them got reduced. Vacuum brake. Vacuum brake is used to stop the railway train in case of emergency. In order to stop the train, the steam at high pressure is made to enter through a pipe into the cylinder of the vacuum brake. Due to this, pressure decreases and the piston of the brake gets lifted, which through a mechanical system lifts the brake. Then Bunsen's burner. In Bunsen's burner, the gas escapes through the fine nozzle and with high velocity, as you can show in the figure. It results in lowering of the pressure in neighborhood of the nozzle. Due to decrease in pressure inside the burner, the atmospheric air enters through the holes, double H. The air and gas mixture rising up produces a flame when ignited. Curved path of a spinning ball. When a spinning ball is thrown with a large speed, then layer of the air moving above the ball gets retarded and layer below the ball gets accelerated due to the spin motion. It is because the layer above the ball moves in direction opposite to that of the spinning ball. On the other hand, the layer below it moves in the direction of spin. Thus, the velocity and hence the kinetic energy of the layer of the air of the ball becomes less than that of below it. According to the Bernoulli's theorem, the pressure energy and hence pressure of the air above the ball becomes greater than below it. Due to this difference in pressure on two sides of the ball, the path of the ball becomes curved. Now, Venturi meter. It is named after the Italian engineer J.B. Venturi. Venturi meter is a device based on Bernoulli's theorem used to measure the rate of flow of a liquid. Pitot tube. It is also a device used to measure the rate of flow of a liquid. It was developed by Henry Pitot and working is based on Bernoulli's theorem. Pitot tube is simply a L-shaped tube which is open at the longer end and has a narrow opening at the smaller end. So with this, we have finished this lecture. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, we are going to end this lecture and thank you.